For this video, I'm just got some three different application problems that have multiple parts, and we're going to be looking at how do we use exponential functions and logarithms in application, and some of the most important being population growth, half-life, and things like that. So for this first problem, we have a couple of models here for the growth and decay of populations for countries. And T is the time in years after 2010. That's important to remember. T is time in years after 2010. So India has 1173.1 e to the power of 0.008 t, and so on for Iraq, Japan, and Russia. So what was the population of Japan in 2010, and what about Iraq? So because we're looking at 2010, that's the same thing as asking when t is 0. Well, we plug 0 in for t for Iraq and Japan, so 31.5 e to the 0.019 t, which is 0. That gives us e to the 0, and anything to the 0 power is 1. 1 times 31.5 is 31.5. And so you actually see that this right here, this number, is the starting population for every one of these models, because it's the same reasoning as this. So for Japan, it would be 127.3, and this is in millions, so it's 127.3 million. And for Iraq, it's 31.5 million. Okay, I'm gonna clean that up. All right. Which country has the greatest growth rate, and what percentage is it? Well, if you remember the formula, A equals P to the times E to the RT, the growth rate is right here. It's the thing multiplying the T. So you see our growth rates is 0.008, 0.019, a negative 0.006, and negative 0.005. So which country has the greatest growth rate? That's the highest number. That's going to be Iraq. It's Iraq. And what percentage is it? Well, it's 0.019 as a decimal number, so a percentage is going to be 1.9%. India has 0.8%. Japan, I'll do 1.9%, negative 0.6%, and negative 0.5%. So that's all the growth rates there. Now, the next question says, which countries have decreasing population? That's going to be a negative growth rate. So Japan has a negative growth rate of negative 0.6%, and Russia, negative 0.5%. The lowest one being Japan. That's decreasing the fastest. Okay, the next question says, when will India's population be projected to be 1377 million, so 1,377,000,000, and then 1.491 billion, or 1,491 million. Okay, to do this, we're going to take the formula that we've been given here. I'm just cleaning up to declutter the space here. We're going to take India, which is this top one here, and we're asking, when is the amount going to be 1377? So 1377 equals 1173.1 e to the 0.008 t. Now, instead of actually solving this, we could solve this for t. I'm going to solve this for a, and that will give me a function of t in terms of a, which is what we want for both of these. It'll make sense when I solve it. So first, let's get the e by itself. So we have a over 1173.1 equals e to the 0.008 t. I need to take the natural log of both sides to get rid of that e. This gives me the natural log of a over 1173.1 equals, and those cancel, giving us just that. Can divide by 0.008, giving me t equal to the natural log of a over 1173.1 over 0.008. Now all I have to do is plug in a equal to that and a equal to that, the 1377 and then 1491, into this function here, this new function that I've created, and I can get both of them right off the bat. So plugging in 1377, we have the natural log of 1377 over 1173.1 divided by 0.008. That gives me t equal to 20.03, and we're going to round to 2 decimal places. I'll just say approximately to make that known. And then for the next one, all I'm going to do is I'm going to change the a into 1491, and that gives me a t approximately equal to, come on, 29.97. T is time in years after 2010, which means it's going to be the year 2030.03, I guess. So it should be like 2030. And then T 29.97 is going to be approximately the year 2040. Once again, all I did there was I plugged 1377 into the spot for A, and then I plugged in 1491 in the same spot. That's how I got those numbers. All right, so populations cannot grow indefinitely as the resources limit, and this is kind of a model that's been created using this data. The data says in 1950, the Earth's population was 2.6 billion people. Then it was 3.0 in 1960, 3.7, and so on. So using this data, this model here was created. And X is the years after 1949. That's important to remember. X is the years after 1949. So this model estimates what the population will be in a certain period of time. And this kind of takes into account limiting resources, things like that. It kind of takes that into account, and you'll see that as we go through the problems here. How well does the function model the data showing the world pop of 6.1 billion for 2000 and 6.9 billion in 2010? So does this model actually follow along with the actual data that's been received? That's the first question here. So to find this, well, we just have to plug in f of, well, x is the years after 1949. So for 2000, this is the same thing as saying x equal to 2000 minus 1949 is 51. And for 2010, that's the same thing as saying x equal to 61. So for 2000, we're plugging in f of 51. We'll just plug in 51 into where x is, 12.57 over 1 plus 4.11 e to the negative 0.02651. Plug it in. I'm going to use a calculator for that. 6.0104. Make sure I plug that all in there. Negative 0.026 times 51. 4.1. Yep, looks good. Okay, so it estimates 6.01 for the year 2000, which is a little bit low, right? 6.1 was the actual data found, right? It was right here. And this one says in 2000 it should be 6 billion. So it's a little low, but it's still pretty close. I mean, it's not like saying 4 billion people. Okay, the next one is plugging in 61. I'm going to use the same formula, except now I'm going to plug it in 61. And that gives us 6.8. 25260. That's the estimation around 4 decimal places. And so this one is 6.82, and that's actually closer to the 6.9 billion that it's supposed to be. So it actually has gotten a little more accurate as it went on. But these are pretty good estimations. Okay, when is the projected world pop 7 billion and 8 billion? So what we're trying to do here is we're trying to figure out when f of x equals 7 and then 8, what is x going to be? Now in the previous problem, in the previous, with the country populations, I solved the function for a different variable. I'm going to do the same thing here. I'm going to do it off the side. It's going to be a little bit, it's not long, it's just the numbers used is they're longer to write out. So I'm just going to solve it off to the side here and bring it back in. So this is the function that, or the model that was given to us. And I'm going to solve this for x. So first thing I'm going to do is I'm going to replace this with y, just so I have one variable to write. And I'm going to multiply both sides by this denominator, 1 plus 4.11 e to the negative 0.026x. I'm just going to multiply to this side as well. That gives me 1 plus 4.11 e to the negative 0.026x times y equals 12.57. Now I can divide by y, subtracting 1. Now I can divide by 4.11. And now I can take the natural log to get rid of the e. And finally, I can divide by this negative 0.026. Now, we're wondering, the problem was, I think 7 billion and 8 billion. Yep. So what we're going to do is we're going to take the 7 billion, the 7, and plug it in for y. And then we're going to take the 8 and plug it in for y. Doing that, so for x, we're plugging in 7. This is just like a shorthand saying x plugged in of 7. Let me plug it in the calculator and see what we get. All right, for 7 billion people, I got 63.15. No, that's probably fine. And then for 8 billion, I got 75.90. This entire process here, you don't have to do this, but if you don't do it, you're gonna have to do it twice, when you plug in the numbers. All I'm doing here is solving for the x variable. That's all I want here, is solving for that. And so by doing this whole process, got it, and these are the numbers I have. Okay, so for 7 billion, we said 63, about 63 years. I'm just going to say 63. And for 8 billion, we have about 76. It was 75.89 or 0.90. Okay, and that makes sense because 63 years, well, this was 61 years. 63 years is going to be 2012. It said 7 billion. Which is about right with the population growth. And then 8 billion is 76 years. 76 years past 1949 is 55 plus 7 is 2005. 2025 is 8 billion, which seems that seems about the same kind of growth for what we've already experienced. So that's what's projected. That's not necessarily what's going to be, right? It's just what's projected If everything stays exactly the same, that's what it says it will be. Okay, according to this model, what is the limit Earth can sustain? Now, how do we find that? Well, think of it like this. The limit that Earth can sustain is the same thing as saying if time continues on towards infinity, right? What's the limiting value for this? Does this thing keep increasing? Does it stop? I don't know. Let's see. And we can test this very easily by saying what happens when x is very, very, very large, like 1 million or a billion or a trillion or a quadrillion, whatever you want to do. You probably could just do 1,000, right? That'll probably be far enough. 100 might even be far enough down the line, but let's just try it, see what happens. But we don't actually need to calculate the value, because we can notice something for the function. In our function here, 12.57 over 1 plus 4.11 e to the negative 0.026, and then x goes right here. Let's just assume we put in 1 million there. Now let's do some like function analysis here. I want to give myself a little bit of room here. Let's do some function analysis. I'm going to look purely at this right here. I'm ignoring the rest of it. I'm only looking at this portion. That's e to some power of x. Now in this case, it's going to be some negative thing, right? Because negative 0.026 times 1 million is like, 26,000, I think. 1, 2, 3, 4, 5. Yeah, 26,000. So it's a very large negative number. And we're going to look at e to the power of x. E to the power of x, if you don't remember, looks like this. Now, we're plugging in a very large negative number. But a very large negative number is just way down here. And this thing, if you'll remember, it asymptotes to 0. That means the further and further we go, the more and more closer it gets to 0 that the function does. So if we keep trying larger and larger and larger values of x, we're going to get smaller and smaller and smaller and smaller and smaller. And essentially, the limiting value, the limit that Earth can sustain, right, is when x goes off to infinity, an infinite number of years. This is assuming, right, everything stays the same. That eventually this thing will just go off towards negative infinity, which gives us this thing goes to 0. So that e function goes to 0. Okay, so essentially this thing just goes to 0, and we have 12.57 over 1 plus 4.11 times 0. But that just also goes to 0, giving us 12.57 over 1, and that equals 12.57. So 12.57 is the limiting value that this model estimates for that Earth can sustain. And that's just using some function analysis, looking at what does e to the power of x go to as the proper mathematical way of saying this is the limit as x goes to infinity of e to the negative x equals 0. That's because we have a negative there. The multiplier doesn't really matter. When you get large enough values of x, the 0.026 is really not really affecting it. What is affecting it is the negative sign. That's what makes it go to 0. This is the way you'd write that mathematically. So 12.57 billion people is what this model estimates for the limit that Earth can sustain. Okay, the last type of problem we're going to be dealing with here is half-life. And half-life is how long a radioactive material decays to half of its present amount. That's what I've written there. What we're pretty much saying here is we're using A equals P to the ERT. That's because radioactive material continuously decays. It never doesn't stop decaying. It is technically not a continuous thing, but it's such a fast rate that it's effectively continuous. So we can use this formula as a good estimation for that. Now, what we're doing is we're saying, what is half of the present amount? That's the same thing as saying A equal to 1/2 P. Well, then this thing just becomes 1/2 P equals P to the RT. And of course, the P's can be divided out to be canceled. That's what gives us this next part. Now to get rid of the, I'm solving here, I'm not solving for anything, I'm just trying to make this a little bit simpler to look at. And the next step is to take ln of both sides, because then the ln and the e cancel. That gives us this part here. And then 1/2 is the same thing as 2 to the -1 power. And if you take the natural log of this, we can bring this -1 down in front, giving us a negative ln of 2. That's what gives us this final thing right here. So to find the half-life of something, we don't need to know the starting amounts or the present amount, or the starting amount or what it should be in the end. We only need to know two things. How long does it decay, and what is the rate of decay? If we know one of those things, we can find the other thing, and so on and so forth. That's what we have here. That's what this table is here. So I have 6 different radioactive materials: tritium, krypton-85, radium-226, uranium-238, arsenic-74, and calcium-47. We know some parts of the table, and we don't know the others. And we're going to find that using this formula here that I derived. So for tritium, we have a half-life we don't know, and we have, I'm going to write this again. This is the negative natural log of 2 equals R times T. So we know the rate of decay. We don't know the half-life, but that's fine because we can find that. Negative natural log of 2 equals the rate of decay is negative 0.055 times T. So to find T, I can do this a little bit simpler. I can solve this thing for both T and R really quick. T equals negative natural log of 2 over R, and R equals negative natural log of 2 over T. So that's the same thing as solving this for T, but I can do that by just saying I don't know what T is, and these are R. So T equals negative natural log of 2 over the rate, which is negative 0.055. The negatives cancel. We get natural log of 2 over 0.055, giving us 12.60, oh, 2 decimal places, 12.60 years. That's how fast it decays. Oh, well, that's how fast it, half of it decays. So if it had, like, I don't know, 60 grams of tritium, then in 12.6 years you should have 6 grams of tritium because it decayed half of it. Okay, for krypton-85, that's the same thing as saying natural log of 2 divided by the rate, which is 0.063. Doing that, 63 gives us 11.00, so about 11 years. All right, now for radium, uranium, arsenic, and calcium, we just need to find the rate instead of the years of decay. So here, the rate is negative natural log of 2. I'm looking at radium-226. Over the time, it takes 1620 years. So we have 1620. And then this is, of course, it's going to be a negative number because the rate is decaying. It gives me 0.12342. Let's see, we'll go 428. So the rate is negative 0.0. You could say it as a percentage. Maybe like a negative 0.0428%. Either way, it's fine. Next, the rate for uranium is negative natural log of 2 over 4560. giving me negative 1 point. I'm getting it in, I'll just write out what I have on the calculator, times 10 to the negative 4. On the calculator, it looks like this, 1.520. There's a bunch of decimal numbers that I'm not writing down. Then it has an e negative 4. That's the same thing as saying 10 to the negative 4. And so really what this thing becomes is negative 0. It goes 1, 2, 3 places. Oh, sorry, 4 places. So we have 0, 0, 0. There's a decimal point. So we have a negative 0.000152, which is the same thing as saying 0.0152%. Okay, we have a rate. In this case, we have 17.5 days. We don't want days. We want years. Yeah, so I'm going to first change this into years by saying 17.5 days. I'll do it off to the side here. 17.5 days is the same thing as how many days per year. If I do this division, there's 365 days in a year. That'll give me how many years 17.5 days is. 365 gives me 0.0479 for the years. Okay, and doing this gives me this is going to be interesting, 14.47 approximately. And this is a very large rate. This is actually going to be as a percentage 1447%. Very fast. It's super fast. 113 hours is the same thing. 113 divided by 24 is the same thing as 4.7083333 days. So I'm going to do 4.7083333 over 365 to give me how many years that is. I get 0.1281290. So the final rate 0.0. I forgot a 0 there. It's supposed to be 0.012. It needs to be smaller than this number, right? So the final amount should be larger than 14.47 since it's a faster rate. I'm getting negative 53.73, which is negative 5373%. This is a super fast rate of decay. Calcium 47, I mean, if you let it sit out for a week or so, you're going to have more than half the amount missing because it decays so fast.